Okay, good afternoon. So first of all, announcement. So I guess you have already received your assignment this morning. So we will have assignment 3 released today. So the deadline will be next Thursday. So please plan ahead and then work it out. So there are a couple of questions. I guess 7 to 8 questions, but they, a lot of them are basic questions. So you should be able to finish them very quickly. Okay, so today we will talk about a new topic. So we will briefly review some of the methods that allow us to prove things nicely. So today we will talk about the technique of mathematical induction, and if we have time, then we will next talk about the method of proof by contradiction, and finally we will talk about the proof by construction. Okay, so what is mathematical induction? Okay, so mathematical induction is this idea. So it's suppose that we want to show there is a certain kind of statement that has a parameter n there. So let's say P is a statement that has a parameter n there. For instance, so P may be a statement like 1 plus 2 plus 3 up to n will be equal to n times n plus 1 divided by 2. So this is a certain statement. And then for some reason, we believe that this statement is true for n is equal to 1, n is equal to 2, n is equal to 3, or n is actually equal to any positive integers. So if you plug in the value of n is equal to 1, then the left-hand side will be 1, and then the right-hand side will be 1 times 2 divided by 2. So it is 1, okay? And then when n has a value of 2, the left-hand side will be representing 1 plus 2. The right-hand side will be representing 2 times 3 divided by 2, which is 3 on both sides, okay? So we want to show that this is true for all possible n's. But if we try to prove this one by one, then we will need infinite number of statements. So the mathematical induction technique is to allow us to prove this to be true for infinite case just by proving 2 or a constant number of statements. So for instance, for this one, we are going to show something called the basis case. So the basis case here is when n is equal to 1. So we want to show that P1 is true. So P1 is the basis case, and then we want to show that this is true. We also want to show that the inductive case. So what is an inductive case? Inductive case, so we want to show that the basis case is true, and we also want to show that the inductive case. So inductive case is something like Pk implies Pk plus 1. So inductive case says, if we assume that Pk is already true, then we will have Pk plus 1 will be true. Okay? So the target for mathematical induction is to show just these two cases, the basis case and also the inductive case. These two cases are true. Then by showing that these two are true, then we will have the consequence. So combining these two, we will know that P1 is true. Is that okay? Now we have P1 is true, and say we have also showed that this one is already true, then we will have P1 true, so P1 implies P2 true, so we will have P2 will also be true. Is that okay? If you understand what I'm talking about so far, could you please raise your hand? Okay, excellent. Now we have P2, and then we have also this one. P2 implies P3. So actually, the inductive case, we should specify a little bit more. We actually show that, okay, we actually insert this one for all k, Pk implies Pk plus 1 is true. So P1 is true, and we also have P1 implies P2. So this one combined with this one, we get P2. And then we have P2, and we also have P2 implies P3. So together, we will have P3 to be true. Is that okay? Then this idea, it can go on forever. So for any particular integer n, let's say n is equal to 100, then applying this logic reasoning 100 times, then you will see that P100 will also be true. So in that sense, all the possible values of n, all the possible positive values, positive integer values of n, will make Pn to be true. Okay? Is that okay? So this is the idea of mathematical induction. So this is a basic form. So today we will take a look at some of the examples here. Okay. Okay, so how about this one? So we just have this example, right? 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2. We want to show that this is true. Okay, so we can prove that this is true by induction. Okay. So first of all, P1 is true because 1 is equal to 1 times 1 plus 1 over 2. Is that okay? And then we want to show that the inductive case is also true. So how do we show the inductive case is also true? So we can first assume that Pk is true. And then hopefully, after some arguments, we can get Pk plus 1 is also true. Once you have this one, then we have under the assumption Pk is true, Pk plus 1 will be true, so we will have the inductive case to be true. So this is our target. So we assume that Pk is true, so what do we have? 1 plus 2 plus 3 plus everything up to k will be equal to k times k plus 1 over 2. Is that okay? Is that okay? And then what do we do next? So we try to find out whether Pk plus 1 will be true. So we will try to compare 1 plus 2 up to k plus 1, whether it is going to be equal to the desired form. Okay? Then, so we have this one to use. So then, this is what we try to examine. Okay, so we add everything up to k plus 1, right? And then hope that we get the desired form. We don't need to do this from scratch. This is the power of induction because we have assumption. We assume this to be true, so we can make simplification based on this assumption. So suddenly, we can simplify this as, because the first part of this one is exactly equal to the first part of this one. So under the assumption, we can replace that by k times k plus 1 over 2. Is that okay? And then plus this k plus 1. Is that okay? So this will be equal to if you combine these two together, we will have k plus 1 times k plus 2 divided by 2. Is that okay? Okay? This is what we hope. So Pk plus 1 is true. So we are not saying that Pk plus 1 is always true. We are saying that Pk plus 1 is true under the assumption that Pk is true. Is that okay? And this is exactly the inductive case. So if we want to continue, thus the inductive case is also true. So basically, this is the end of the induction proof. But to make everything that makes sense to a reader, we will usually end up by saying that by the principle of mathematical induction, the statement Pn is true for every n is equal to 1, 2, 3, and so on. Okay, so this is the conclusion of the proof. Okay, so this is a beautiful proof. Very short. We just need to prove two statements, but then we are showing this important result. It is true for every value of n. Okay, good. Okay, let's do another example. So how about this one? Okay, so I'm going to wipe this out. So this time, let's try another statement. Okay. Okay, let me use. Let's try this one. So we have a Qn, which is the statement about another thing. So let's say Qn represents this statement. Let's say 1 plus 3 plus 5 plus ... Let's say they are altogether n terms. So n terms. So the last one will be what? 2n minus 1, okay? It's going to be equal to n squared. Okay? Yeah. So we prove this. Okay? So we can prove this. This is another example. So how about, so the proof will be what? So Q1 is true. Okay, you don't need to give reason. It's trivial. But if you want to give reason, then since you copy it, so since 1 is equal to 1 squared. Okay? Okay? Now, so you don't need to copy the statement here exactly. Use your own word. So Q1 is true. Next, you can say for the inductive case, so we assume that Qk is true. So what is meant by Qk is true? So that is, if I have 1 plus 2, no, this is 1 plus, okay, 1 plus 3 plus 5 plus ... plus 2k minus 1 is equal to k squared. Is that okay? Then, what do we want? We want to see what happens when we are considering the statement when n is equal to k plus 1. We want to show that pk plus 1 would then be true under this assumption. Okay, under this assumption, so pk plus 1 will be, we will look at what? 1 plus, and then we need to look at one more term. So this term will be 2k plus 1. Okay? And then this is equal to k squared plus 2k plus 1. And then if you worry that the reader do not know why you get an equality here, you mention this. This is by the induction assumption. So by this induction assumption, or sometimes we call it the induction hypothesis. Okay? So you make a mark here. So this equality comes from induction hypothesis. And then this is going to be equal to k plus 1 squared. And then if you want to make a reason for this one, this is just simple algebra. Okay? Okay, good. This is exactly the form of Qk plus 1. So we can have, so Qk plus 1 is true. And then what do we need next? So we need to complete the proof by writing 2 more lines. So we will need to tell the people that at this moment, the inductive case is also true. And because you have already shown the basis case and also the inductive case, then you can use the principle of mathematical induction to show that everything is OK for n is equal to 1, 2, 3, up to infinity. So far, so good, right? So far, so good, right? Let's do one more. OK, let's do one more. Let's do this one. OK, so how about this time, let's have R. Let's say R represents the statement, OK, that this time, let's say you have 1 square plus 2 square plus 3 square. You have n times up to n square. This will be equal to n times n plus 1 times 2n plus 1. You divide this by 6. OK? OK, you want to show this? OK, we do this again, just as a practice. So we do this again. So the proof, we want to show that this is true for every positive integer n. So the proof is like, OK, R1 is true. And then if you are lazy, yeah, you can just write down, this is so trivial. You don't need to do anything, trivial. OK, just plug in 1. 1 times 2 times 3 divided by 6 is equal to 1. 1 square is 1, so it is true. OK. Next, we assume that Rk is true. We assume this. Then we are interested in about Rk plus 1. So we can start by looking at what happens for Rk plus 1. Rk plus 1 is you add up to k square, and then you add k plus 1 square. So this will be equal to, because we assume that Rk is true already, so the first, this part you can simplify as k times k plus 1 times 2k plus 1 divided by 6. And then you have k plus 1 square. And then this equality is due to this assumption. OK? And then what is next? Next is algebra. OK. So this is equal to what? Everything has k plus 1, so you can take out k plus 1. OK? And then let's say we take out k plus 1 divided by 6. And then what do we have? This one you will have 2k squared plus k. Is that OK? And then this one, you take out k plus 1 over 6, so you will have 6k plus 6. Am I correct? Is that OK? OK, so let's do this. So this is like 2k squared plus 7k plus 6. Am I correct? So we need to do factorization. And then it turns out that this is like 2k plus 3 times k plus 2. 2k plus 3 times k plus 2, yes. So this is equal to k plus 1 divided by 6. And then this one is equal to 2k plus 3 times k plus 2. Is that OK? Yeah, 2k squared, 3k, 4k, so you get 7k. 3 times 2, you get 6. So this is it. OK, and this is exactly the form that we want. So we will need to complete the proof by saying that, OK, Rk plus 1 will be true. So the inductive case is true. And then by the principle of mathematical induction, then this R statement, Rn, will be true for every n is equal to 1, 2, 3, up to infinity. Is that OK? OK. Now, so this is about mathematical induction. So the powerful thing here is you just need to prove constant number of statements, finite number of statements, and then you can show infinite number of cases to be correct. But there is one weakness about mathematical induction. Mathematical induction does not create knowledge. So you need to you have some idea about what it is like. And then you are going to confirm that it is correct. So if you don't have this side, 1 plus 3 plus 5 plus 2n minus 1, I want to get a formula for this one. I don't know. It doesn't tell us what it is. But on the other hand, if you really know that this is equal to n squared, or if you guess that it is equal to n squared, then you can confirm whether you are correct by making a guess, and then show by mathematical induction formally that it is correct. So it is powerful, but it is not that a good general technique to help you to solve a problem. It is to show that something that you know is really correct. Is that okay? Okay. Now, for this, so later we will see a few more examples of mathematical induction. It does not need to be that boring. We are not going to show everything by mathematical induction, like statements like 1 plus 2 plus 3 up to n, or the Fibonacci sequence, or whatever, sum of Fibonacci numbers. So we will see some more examples.